Nuclear magnetic resonance is a technique that uses magnetic fields and electromagnetic frequencies to study molecular structures. For high magnetic fields, superconducting magnets are used. Lower fields can be generated by permanent or electromagnets. Samples are inserted in the center of the magnet and are positioned in the NMR probe. So the sample is located at the position of the strongest field and highest homogeneity of the magnet. The NMR probe consists of coils that are used to excite the sample and record signal responses at radio frequency. The basis of NMR is that nuclei behave like microscopic magnets in a magnetic field. They spin around the main magnetic field just like a spinning top. This motion is called precession. The frequency of the precession is proportional to magnetic field strength. Additional local field differences are introduced by changing electron densities in a molecule. A higher electron density results in more shielding and thus a lower local field and lower spinning frequency. In NMR, the frequency of the excited nuclear spins can be measured from the electric current they induce in the coil. Fourier transformation of the time domain signals results in the frequency spectrum, with a signal for each different nucleus. The different frequencies we call chemical shifts, as they depend on the chemical structure of the nuclei. In practice, spectra are measured for all hydrogen nuclei at once, which results in the ethanol spectrum with 3 different peaks at different chemical shifts. Since nuclear spins behave like magnets, they also influence their neighbors. One way this happens is through shared electrons in the chemical bonds in the molecule. We call this J-coupling. Each spin can have 2 states, along the magnetic field or against the magnetic field. As an example, we look at the 2 methylene hydrogen spins, which are chemically identical. They can have 4 combinations: 1 spin down, 1 up, both spins down, 1 up, 1 down, 2 spins up. Each combination has a different energy level and influence on the neighboring spins, except that up-down and down-up combinations have the same energy level and influence. The influence is visible as a splitting of the signal of the methyl group into 3. This is called a multiplet. Likewise, the 3 methyl hydrogen spins split the methylene response into 4 signals. In conclusion, NMR can identify molecular structures from chemical shifts and multiplets.
Nuclear magnetic resonance, or NMR, is probably the most important technique for finding the structures of organic compounds. So much so that there is a saying, when the NMR goes down, the organic chemists go home. The principle of NMR is based on the fact that certain nuclei with odd atomic mass or atomic number, such as hydrogen-1, carbon-13, fluorine-19 and phosphorus-31, have a property called spin. This means that they have a magnetic field similar to that of a bar magnet. When placed in an external magnetic field, these nuclear magnets can line up in one of 2 ways, with or against the applied field. These 2 different states have slightly different energy levels. Electromagnetic radiation, which has an energy corresponding to the gap between these 2 states, can cause these nuclear magnets to flip from a low-energy state to a high-energy one. The size of the energy gap determines the frequency of radiation required. Each element has its own particular frequency, but they all lie within the radio part of the spectrum. We will concentrate on hydrogen-1 NMR. This is often called proton NMR because the hydrogen nucleus is just a single proton. they drop back from higher to lower energy states, the nuclei of hydrogen atoms in different positions in the molecule give out energy at slightly different frequencies, and this can tell us a lot about the structure of the molecule. For example, in ethanol, CH3CH2OH, the three CH3 hydrogens will give a slightly different frequency than the two CH2 hydrogens, which will be different again from that of the single OH hydrogen. This energy is picked up by a receiver in the instrument and looks like this. A strong signal gradually dying away. This is the total signal from all of the hydrogen nuclei in the sample and is very difficult to interpret. However, a mathematical technique called a Fourier transformation can be used to separate out the signals from hydrogen atoms that are in different molecular environments and present them as a spectrum that can be interpreted by chemists. This is a typical NMR instrument. The magnet is a superconducting one and is housed inside the cylindrical metal casing. It is cooled to 4 Kelvin in a jacket of liquid helium, which in turn sits in a jacket of liquid nitrogen at 77 Kelvin. The magnet uses a current of 50 amperes, which, once started, flows continuously as the coils have zero resistance at 4 Kelvin. The sample sits in the centre of the cylinder inside this probe, which contains the coils that send and receive the radio frequency signals. The electronics which generate and interpret the radio signals are housed in the boxes to the left. Samples are placed in the machine and removed from it by the auto changer, which takes the samples in turn from the carousel. The instrument is controlled from this workstation. This bare probe shows the radio coils and where the sample sits. Here we will run the proton spectrum of ethanol. A small amount is taken and dissolved in deuterated trichloromethane. This solvent is trichloromethane, in which all the hydrogen atoms have been replaced by deuterium. This is so that the signals from hydrogen atoms in the solvent will not be mixed up with those in the sample. A little tetramethylsilane, TMS, is often added as a reference. Each molecule of this has 12 hydrogen atoms, all in exactly the same environment. The signal from these is taken to be the zero of the spectrum and has the value of 0 parts per million. Inside the instrument, the sample sits on a cushion of gaseous nitrogen. This plastic spinner has vanes that turn in the flow of nitrogen and spin the sample. The spinner is placed on the tube in such a position that the sample tube will be in the centre of the magnetic field when it is in the instrument. Together, these ensure that the sample experiences a uniform magnetic field. The operator places the sample in the auto changer and tells the computer the identity of the sample and which position in the carousel it is in. The auto changer selects the correct sample and places it in the instrument. The sample is lowered gently into the probe on a cushion of nitrogen so that it sits in the centre of the magnetic field and the radio coils. Under the control of the computer, the instrument applies several, typically 16, pulses of radio waves to the sample and collects the responses, called resonances. These resonances are summed up by the computer and processed to give a spectrum. This takes about 5 to 10 minutes. Here is the spectrum of ethanol. The peak to the far right is that from the TMS reference. By definition, this is at 0 parts per million, ppm. The distance leftwards along the horizontal axis is called the chemical shift, and it is measured relative to the peak that is obtained from the hydrogen atoms in TMS. The chemical shift of a peak gives information about the molecular environment of the hydrogen atoms that it represents. The peak at around 1 ppm is caused by the CH3 protons. That at approximately 1.6 is the OH proton, and that at approximately 3.5 ppm is from the CH2 protons. The area under each peak is proportional to the number of each type of proton. This is calculated by the computer and represented by the step height of this integration trace. A closer look at the spectrum shows that the peaks are in fact split into groups of peaks called multiplets with particular patterns. This is called spin-spin splitting. It is due to the influence of the magnetic field of adjacent protons. Two adjacent protons split a peak into three, with heights in the ratio 1 to 2 to 1. And three adjacent protons produce four peaks, with height ratios 1 to 3 to 3 to 1. This is sometimes called the n+1 rule. Interpreting proton NMR spectra can thus provide a great deal of information about molecular structures. The same instrument can be used for NMR of other magnetic nuclei. A useful one for organic chemists is carbon-13 NMR. All that has to be changed is the frequency of the radio signals.
Magnetic resonance imaging, commonly known as MRI, helps doctors find, watch, and treat medical problems. MRI uses very strong magnets, radio waves, and a computer to make pictures of the inside of the body. MRI pictures are more detailed than those made with other methods. There are many reasons to have MRI. MRI may find bleeding, such as bleeding in the brain, brain changes, as in stroke, problems with your back, such as a herniated disc, and an injury inside the body, such as a torn anterior cruciate ligament. Before MRI, you will remove all metal objects. And it's not safe to have MRI with some medical implants. You should tell the MRI technologist about any metal, device, or implant you may have in your body, such as a pacemaker. To prepare for MRI, you will lie on a table just outside the scanner. MRI scanners are very noisy, so you will probably wear earplugs or headphones. Different equipment, such as pillows and straps, will help you stay in the correct position. Once you are ready, the table will slide into the scanner. Most often, closed scanners, such as this one, are used. The area inside is very narrow. In some areas, open scanners are available. This scanner is open on the sides, so you won't be completely surrounded by the machine. However, the pictures may not be as good as with closed scanners. For either type of scanner, a technologist will operate it from the next room. You will be able to talk to each other through a two-way speaker. During the scan, magnets in the machine will create a strong magnetic field. This will not harm you. Then, the scanner will send radio waves through your body. This will not harm you. When the radio waves are turned off, the scanner will pick up energy signals from your body. These signals are used to make the pictures. During the scan, you will have to stay very still so the images will be clear. You may be asked to hold your breath for a short time. MRIs may take 30 to 45 minutes or longer to complete. In some cases, you may get contrast dye with your MRI. The dye helps make clearer pictures. After the MRI, you can resume your normal activities. If you received contrast dye, the technologist may ask you to drink plenty of water or other healthy drinks to help your kidneys remove the dye from your body.